Hello chemistry students and welcome to lesson 5.08 honors dealing with colligative properties. To be in this session you of course have already completed the 5.08 regular assignment where we really are just defining colligative properties and the relationships there. In this assignment we're actually going to look at the calculations that are involved with colligative properties. Before we do that, let me just mention the objectives. Again, there are common core standards that we are going to address in this lesson. And you can pause the video at this point and read over them if you would like. You can also access these in the course information section and click on standards. For this particular lesson, our objective is to explain how the amount of solute will affect colligative properties of a solution. Now, of course, I did mention that you should have already done the regular assignment 5.08. You also need to make sure that you are understanding lessons 5.5 and 5.6 dealing with solutions and concentration. Again, if you are still unsure about those particular lessons, please go back and review them. Watch the videos, attend the tutoring sessions if you need, but make sure you are comfortable with those lessons prior to doing the 508 honors, so it'll, of course make sense, but you'll also have a more successful experience going through that lesson and be able to learn the concepts in there. Now again, I mentioned that this time around we're going to be actually calculating. Okay. Now remember there are three colligative properties that we work with: vapor pressure lowering, boiling point elevation, and freezing point depression. When we're doing our calculations, we are only going to be focusing on those last two: boiling point elevation and freezing point depression. So let's look at the formula here. Boiling point elevation, again, is related to the concentration of the solution. And remember, in the 508 assignment, we talk about how we measure it in molality, because molality deals with the number of particles dissolved, not the volume of solution, where that's what molarity does for us. So that's why we came up with this new one called molality. So we need to look at the relationship between the boiling point mean change and the molality. And that is right here in this equation. Delta T B equals KB and then the cursive or italics M. So let's kind of break that apart here for a moment. Delta is a Greek symbol that we use in chemistry to mean change. So when we say delta T, we mean the change in temperature. The subscript B tells us that we're dealing with boiling point. So this whole expression, delta TB, simply means the change in boiling point temperature. K is the symbol we use for constant. So KB is the molal boiling point constant. If you look down here, the second bullet point, each substance has its own molal boiling point constant. Of course, most of our solutions that we work with are in water. So we did mention here that the molal boiling point constant for water is 0.51 degrees Celsius per molal. But again, every substance is different, so if you ever are coming across a practice problem where you're giving a different solvent, be sure that you're using the correct KB. Don't just assume it's always water. You make sure you read the question. Alright, and then the italics M represents molality. And remember, we did a problem with that back in the last lesson, 508, and molality again is just the moles of solute over kilograms of solvent. Alright, so again, once we have that molality, we can simply multiply it by the constant, and that gives us the change in temperature. Now, since again most of the time we're working with water, just a note, remember that the regular boiling point of water is 100 degrees Celsius. So when we say change in temperature, let's say that number comes out 3 when we solve the equation. Then our new boiling point of water is 103 degrees Celsius, because remember it is boiling point elevation, So we have to add it to the regular boiling point of 100. And again, that's if we're working with water. If we're working with another substance, then we would add it to whatever that substance's boiling point is. All right, so calculating it. All right, what is the expected change in boiling point when 135 grams of C6H12O6 sugar are dissolved in 1.5 kilograms of water? The boiling point constant for water, again, is 0.51 degrees Celsius per mole. All right, so again, our formula, all right, was delta T B equals KB times the mole. All right, so the KB we already know. That's 0.51. We need to figure out the mole. Okay, so again, the molality. All right, now the kilograms of solvent we are given up here, 1.5. So that part we already have. So we need to take our 135 grams and convert that to moles. All right, and again, our solute here is C6H12O6. All right, so we got to go to our periodic table and look up all of those masses and add them together. All right, so carbon is 12.011. And there are 6 in the formula, so we have to multiply it by 6. And then we add that to 12 hydrogen, so 1.0079 times 12. And then add that to the oxygen, 15.99 times 6. And that would give us 180.1 grams per 1 mole. All right, and again, that's going back to module 3, that molar mass. We take the mass of carbon, multiply it by 6, mass of hydrogen, multiply it by 12, mass of oxygen, multiply it by 6, and then add those 3 numbers together, and you get 180. So you take 135 divided by the 180, and that gives us our moles, which is 0.766. All right, so we go back up here, plug that in here for our moles, and the kilograms again is 1.5, so that gives us a molality of 0.511. Okay, so now back up to our first equation, the original equation up here. KB we already know again is 0.51 degrees Celsius per mole. The molality we just determined was 0.511. Okay, so our change in temperature here is going to be 0.26 degrees Celsius. Okay, now again, that is our change in temperature. All right, and the question asks us what is the expected change. So that would be our final answer. But if the question asked us, well, what is the new boiling point, then we would have to add this to 100. Okay, so if the question asks for the new boiling point, I'm going to put this down here on the bottom. Okay, if the question wants the new boiling point, and again we would need to add that to 100. So of course 100 plus 0.26 is just going to be 100.26 degrees Celsius. Alright, and that again is if the question asked us to do that. So let's look at a situation where it does break up into those ions and see how that would slightly change our calculations. Alright, what is the expected change in boiling point when 25 grams of BaCl2 are dissolved in 750 grams of water? And again, the boiling point constant is 0.51. Alright, well first off, let's look at what we end up with here for particles. We got BaCl2. So when we dissolve that in water, we're going to have, reversing our crisscross, we're going to have barium with a +2 charge, and we're going to have 2 chlorines with a -1. So total, we have 3 particles. Okay? Now that's going to come in when we get to the molality, because remember, our molality is going to be 3 times that, because for each particle of BaCl2 that's dissolved, we're actually getting 3 particles in solution. Okay, so let's go to our molality. Remember, that's the first thing we needed. And we have 25 grams. We got to first get that into moles. Alright, so again, we do need our periodic table, and we need to look up the molar mass of those 2 elements. So for barium, we have 137.33, and then we add to that 2 chlorines. Alright, so 1 chlorine is 35.453, and then we would get a grand total of 208.2. Alright, again, our molar mass, so we need to divide by that. That way we get grams on the bottom, moles on top. So the grams will cancel. Alright, and that gives us 0.120 moles. Okay, but again, when we dissolve it, it actually is going to be 3 particles for each mole dissolved. So we have to multiply that by 3 to get our total particles in solution here. So really we have 0.360 moles of particles. And because now it's not BaCl2, it's Ba and 2 Cl2s. Okay, so we'll just say particles. Alright, now they also gave us the 750 grams of the water. And remember, we need that in kilograms. And again, going back to our metrics back at the beginning of the course, we remember that there is 1,000 grams for every 1 kilogram. So that's going to give us 0.75 kilograms. Okay, so now to get our molality, alright, we just simply take our moles 0.360, and then divide it by our kilograms. Alright, and that gives us a molality of 0.488 molal. Alright, so now we're just plugging into our formula, right? So delta TB equals 0.51 times 0.48. And in this case, our delta TB is 0.24 degrees Celsius. And again, if it asks us for the final temperature, then we would just add that to 100. So we'd have 100.24. Okay, so you can see that since we added such a small amount, we only added 25 grams, you can see it didn't have a huge impact overall, even though we're getting 3 particles per each one there. All right, so again, we got to convert to moles. When it's an ionic compound, remember to multiply by the number of particles to get the total moles of particles in solution. And then you use that in your calculation to figure out the molality. And then, of course, just plug into the formula to get the delta T. All right, now when we're doing freezing, it's a very similar formula. Okay, for freezing point, remember it is, sorry, that should not be elevation, that should say depression there. All right, it's going down. Okay, remember we talked about in the regular lesson that when you are adding salt to a solution, it interferes with the freezing process. So it takes longer, so it means the temperature is going to continue to decrease. So it's freezing point depression. And again, it is also directly related to the number of particles. So when we look at the formula here, very similar formula, delta TF equals KF times the molality. Again, KF in this case is the molal freezing point constant, and it is negative 1.86 degrees Celsius per molal. Now in this case, just so you know, the negative sign is simply placed there because since it's a depression, by putting the negative sign there, that just helps us remember that at the end we subtract it from the normal boiling point. Okay, and the normal, or excuse me, normal freezing point. And again, the normal freezing point of water is 0 degrees Celsius. That's the one that we work, most frequently with. So when we do these problems, we're going to be subtracting that number from 0 to get the new freezing point. All right, so let's go ahead and try a couple of those. Very similar calculations to the ones we were just doing. All right, again, it's depression, not elevation. My apologies there for the slides. Okay, that should be depression, not elevation. All right, a solution is made by dissolving 9.8 grams of the sugar again in 275 grams of water. What is the freezing point depression? All right, so just like we were doing earlier, we start with the 9.8 grams of the C6, H12, 0.06. And again, if we go back a few slides, we remember that the molar mass that we looked up on the periodic table was 180.1 grams per mole. Again, we divide by that to cancel out the units. So 9.8 divided by 180.1, and we're going to end up with 0.0544. Alright, again, this is a covalent compound, so it's not going to break up, so we do not have to multiply it by anything, because we're just going to have one particle per each, sugar molecule that's dissolved. So that's not going to change. The 275 grams again, if we divide that by 1,000, that gets us our kilograms. All right, 1 kilogram is equal to 1,000 grams. So we end up with 0.275 kilograms. Now to figure out the molality, we would then simply divide those two. So we got 0.0544 moles over 75 kilograms. All right, and that gives us a molality of 0.198. All right, so now we're looking for delta TF. Okay, the KF, all right, is our constant, 1.86 degrees Celsius per molal, and we multiply that by the 0.198 molal. Alright, and we end up with negative 0.368 degrees Celsius. Now, if they asked us for the new freezing point, okay, because that could be a possible way to word this question, again, we're just subtracting it from 0. So obviously 0 minus 0.368 is still going to be the same thing. So when you're doing water, the delta T is of course also going to be the new temperature. But that's only for water since the freezing point is 0. Again, if you're dealing with a different solvent, you then subtract it from the freezing point of that particular solvent. Alright, so let's try another one. And again, this time we are dealing with, again, depression here. And we are dealing with an ionic compound. Alright, so this time we have NaCl. We're dissolving 25 grams of NaCl in 1 kilogram of water. Okay, so they already gave us the kilograms in this one. They were nice to us on this one. But we got to first get those 25 grams of NaCl converted to moles. But again, we need our molar mass. So we're going to our periodic table. Sodium, 22.99. Chlorine, 35.453. And that's going to be 58.44 grams. And again, that is in 1 mole. Alright, so 25 divided by 58.44. We get 0.4277 moles. Okay, so now again, NaCl, let's go back here, we got slightly ahead of ourselves. NaCl, when we place that in water, it's going to, again, reversing our crisscross, we're going to get 2 ions. We're going to get Na with a +1, and we're going to get Cl with a -1. So in this case, we end up with 2 particles. So we then need to multiply our moles by 2. And that gives us 0.8 5 5 6. And again, this is moles of particles now. Okay, not just NaCl, but moles of particles. So now to get the molality, and we're going to take the moles, .856. All right, we were told in the problem that we had 1 kilogram. So we have 0.8556 molal. So to get our delta TF, and we're taking negative 1.86 degrees Celsius per molal, and then multiplying it by the 0.8556. And that would give us a delta TF of negative 1.59 degrees Celsius. Okay, so again, subtracting that from 0 would give us a new freezing point of negative 1.59. Okay, so again, the kind of a key part here is to make sure you check to see is it an ionic compound or a covalent compound. If it's covalent, then I just work it as is. If it's ionic, then remember to multiply by how many particles you will get to get the total moles of particles, and then continue the calculations from there. All right, another thing that we like to do in chemistry is we like to kind of work backwards in a sense. We like to figure out the the change in freezing point or boiling point, and then we use that information to work backwards and figure out the molar mass of the compound that we're working with. All right, and this is something that we do quite frequently in a lab, and again we use this to actually help determine what we're working with. All right, so basically what you do is you take a known mass of the solute, put in a known mass of the solvent, and then you either cool it or heat it. Okay, if you want to use freezing point depression, you're cooling it. If you're heating it, you're using boiling point elevation. And then you can use the data, all right, basically the change in the temperature to work backwards. All right, so the two formulas we have to use. Well, we're taking the formula that we have been using and we're just expanding it. Instead of saying molal over here, we're just actually putting in the formula for molal. Moles of solute over kilograms of solvent. So it's still delta T, B or F, whichever one you're working with, times the K, and then multiply it by the moles over the kilograms. The other thing we have to use is what we've been using throughout the course. Remember that the molar mass is the mass of solute divided by the moles of solute. All right, so we're going to use both formulas in solving this. So let's look at an example problem here. We have 50 grams of a molecular solute. Okay, so that's important because that tells us it doesn't break into particles. It stays as one piece when it's dissolved. It's dissolved in 25 grams of water. The freezing point of the solution is negative 2.5 degrees Celsius. If the molal freezing point is negative 1.86, determine the molar mass. Okay, so again, using the formula that we had on the last slide there, the delta T they give us, all right, that's this negative 2.5, all right, so we have out in front here negative 2.5 degrees Celsius. That's our delta T. KB, again, we know that it is negative 1.86 degrees Celsius per molal. Okay, on top we have moles of solute. That's what we're solving for, right? That's something they did not give us. And then the mass, okay, of solvent, the grams of solvent. Well, they gave us 25. So let's slide down here real quick. Remember, to get grams to kilograms, what do? That's right, we need to divide by 1,000. Right, 1,000 grams in 1 kilogram. So when you do that, we would end up with 0.025 kilograms of solvent. All right, so I'm going to put this down here. So that means we got negative 2.5 degrees Celsius. Okay, if we go ahead and do the division on the right side, we take negative 1.86 divided by 0.025. And over here, that gives us negative 74.4 times, we're going to say X for our moles of solute. Alright, so to get X by itself, we would then divide both sides by this negative 74.4. Alright, just doing a little algebra there. So that tells us that X is 0.0336, and this is moles of our solute, which our solute, remember, is some molecular substance. And we're trying to figure out what that substance is. That's the whole purpose of doing this. Okay? Now remember, molar mass is grams divided by moles. The problem tells us the grams. Okay, so if we look at the problem here, it told us that we had 5 grams of the molecular substance. So 5.0 divided by 0.0336 moles. Alright, and that gives us a molar mass of 148.8. Alright, so then what we could do is we could then use that value and compare it to a list of known substances and their molar masses and be able to determine what substance it was that we were working with, what solvent we were working with. And that would be something that we would do in a laboratory situation. Alright, so we have completed the lesson. So of course the question is, what's next? Again, you need to complete all example, practice problems, hyperlinks, etc. in the Lessons Honors 5.08 Honors Lesson tab. If you're still needing some more help, please attend the open tutoring sessions. We also have a review sheet, and once you're feeling comfortable with the material, you can then complete the 5.08 Honors quiz. And again, you can access that quiz by going to the assessment section or the gradebook section. Once you have completed this, you can then call your teacher and schedule your discussion-based assessment for Module 5 and be able to wrap Module 5 up and then ready to move on to Module 6. So thanks for joining us today, and hope this was helpful, and we'll talk with you again soon.